So today we have the second seminar in our FAIR seminar series, which is the initiative which aims to disseminate the knowledge about FAIR, which is the Accelerator Center in Construction at Darmstadt, Germany, and is one of the world's largest centers of this type. And the seminar will discuss the main research topics of FAIR, so NUSTAR, CBN, PANDA, and APA, the status of FAIR, and above all, the participation of Slovenian researchers in this project. So today, we have here as a guest Dr. Jürgen Gerl. Dr. Gerl has obtained his diploma and PhD at Frankfurt University. Afterwards, he was postdoc at University in Canberra and then research associate at MPI Heidelberg. He was employed by Robert Bosch for 2 years, and since 1999, he is a scientist at JSI at Darmstadt. He is the head of nuclear spectroscopy department at JSI Darmstadt since 1999, and he is the leader of FAIR NUSTAR project since 2016. He is also NUSTAR project manager and technical coordinator. Dr. Gerl has over 300 publications and 6 filed patents. He supervised more than 37 PhD students and more than 18 postdocs. His research interests are experimental nuclear structure physics, heavy ion physics, instrumentation and methodologies, and technological applications. So today, Dr. Gerl will tell us about the research opportunities and perspectives of NUSTAR and FAIR. So Jürgen, please.
Thanks, Jelena, for this nice introduction. And let me see if I can get things started. Oh, now everything should be full screen. No, I think it works. So first of all, thanks a lot for this nice invitation. And I have to say, this is now the first travel since 3 years. Before COVID, I could not, we all could not travel. And so it's a particular pleasure for me to have now this first opportunity that we are allowed to travel again and to Josef Stefan Institute. I was here several times, so I know the place and I know you. So it's always nice to be here. And in particular now that we can start FAIR relatively soon, hopefully. So it's also important to be here and to strengthen our connections. And today, I will talk about the research opportunities you can have at FAIR, in particular with nuclear structure physics or nuclear physics in general, which is this NUSTAR project. Now, before I come to NUSTAR, let me briefly, for some new members of the Institute here, introduce also JSI. So JSI is a German national lab. We have currently about 1,600 employees, roughly 1,000 guest scientists per year from all over the world. And we are dedicated to heavy ion research. So we are operating accelerators, a linear accelerator called UNILAC, and a synchrotron called CIS, which provides us beams from protons up to uranium in an energy range from 14 MeV, this is the UNILAC range here, up to 2 GeV per nucleon. And our research areas are nuclear physics, atomic physics, biophysics and medicine, material research, instrumentation, and also applications. So JSI is well over 50 years old, 53 to be exact, and was founded 50 years ago for German universities, because at that time it was fashionable to have an accelerator, but most of the institutions, they could only afford small funding crafts like the one which you are running here. But there was the idea to have really heavy ions and go also with to much larger energies, and this was no longer affordable. And so the universities in the surrounding of Frankfurt and Darmstadt, they decided to cooperate and build an accelerator by themselves. So they convinced the Federal Ministry for Research to give them some money, and then the mayor of Darmstadt was quite generous, so he gave us this ground here, and later on it turned out that this is a swamp. So anyhow, he could not do anything else with this area. So, but nevertheless, the physicists at that time were quite happy to have a place at all. And so in the forest north of Darmstadt, we started JSI. And so this was quite a successful story. And soon afterwards, already in the 70s, it became an international facility. We had guests from all over the world and were quite successful in our research. And so some 20 years ago, the BMBF, also our research ministry, told us, well, you are so nice and so doing so nice physics. Now, what are your dreams? So tell us what would be the dream facility. And the dream facility for us was a machine which would have much higher intensities, much higher energies. And so we made a sketch of such a facility. And what BMBF told us also, it should be something above 1 billion euro. Otherwise, if you come with something small, a modification, we will not buy or we will not fund you. But if you come with something really great and really international, then we will fund it. And so we said, well, then let's go for FAIR. And indeed, it was in the beginning above 1 billion. Meanwhile, we are far above 2 billion. We are approaching 3 billion in total cost. So this is what the government wanted. And we said from the very beginning, it should be a multinational. So FAIR is now our future. It will be the largest heavy ion accelerator complex in the world, which provides stable and radioactive beams of all elements, plus antiprotons. This is new for JSI. We will have ion storage rings and, of course, unique experimental setups. So this is how this facility looks like. Here you see the old part in blue. The only new addition which is already running is the Ring. This is a donation from Sweden, which is an ultra vacuum, very low energy storage ring for heavy ions. But all the rest here is really completely new. We have a synchrotron Cis 100, also 100 Tesla meter bending strength. We have a super fragment separator for generating exotic ions. We have two storage rings, the CR and the HESR, and we have several experimental stations for the different experimental programs. So we can, as I said, we can accelerate everything from protons up to uranium. There will be an intensity upgrade, increase of up to a factor of 100 with it. So for instance, the uranium beams, we would like to get up to 5 times 10 to the 11. And particularly for radioactive beams, so all these isotopes far of stability, we expect an intensity upgrade of 4 orders of magnitude, a factor of 10,000. Of course, you can imagine this is a new type of physics that you can do with such a facility. And this is where we in NUSTAR mainly work with. But one could also have high pulse powers. So one could get very short pulses, 50 nanosecond pulses with 50 kilojoule. So this is really a lot of energy which you put in a very short time period for plasma physics experiment, for instance. In addition, we have all this suite of storage and cooler rings. I can't go into all these details. I guess 2 weeks ago or whenever that was, our managing directors told you already what we can do. But anyhow, as we would like to perform forefront experiments towards the production and investigation of new extreme states of matter. So this is our grand idea that we would like to do. Of course, one cannot do it alone. So this is now a truly international thing. And here normally I would have now a world map, but intentionally I did not take the world map here to show you how international we are, but rather I put the funding people they signed as a FAIR convention in October 2010. And the reason why I did it is twofold. First of all, on a world map, Slovenia is much smaller than actually your contribution to FAIR, and so would be unfair. And the second reason is our second largest shareholder is Russia, and currently, as you know, we have frozen all contacts with Russia, and therefore I think it would not be appropriate to show now the largest landmass on the Earth, which is Russia, on such a map, and therefore I've decided now to show you rather the people. Unfortunately, I don't know who signed for Slovenia. I think it was a lady, but I can't figure out who. Maybe you can identify her. Anyhow, we have 9 shareholders plus UK as an associated partner. Slovenia is one of the shareholders. We have more than 200 institutions from 33 countries who are involved with their scientists in FAIR. So more or less all the developed world is somehow associated with FAIR. So to go into some detail, yeah, it's big. This I told you already. The actual construction area is 96 soccer fields. The total floor space is the size of a mid-sized airport. And I mentioned already that we are sitting on a swamp, and this made it necessary to have concrete ground piles in the ground. So we have 1,300 ground piles to stabilize the floor with a total length of 60 kilometers. What is amazing is since we have to go underground with most of the facility, we had and still have to excavate 1.2 million cubic meters of soil. So that's, also if you haven't seen it, and I invite everybody really to come to Darmstadt and have a look yourself. It's really amazing. Groundbreaking was in 2017, and this is how it looks now. It's only a figure of the central site. Probably you saw one of these videos where you can get a nice overview of the whole facility. As I said, it's really amazing, and it's also amazing how fast it progresses. And we expect to be ready in about 3 to 4 years with the facility itself, if everything goes well. It's not only concrete, it's also high-tech machines. What was new for us is that we have to deal with a lot of superconducting magnets. The reason for that is we cannot afford the electricity if we would go normal conducting. Already now, until recently, we paid something like 10 million euro per year for electricity. Now, with these problems we have internationally with power, it went up to 16 or 18 million. Now you can imagine with such a big facility, we would pay more than 100 million only in electricity, which is of course impossible. But if you run superconducting, then of course the power for the magnet goes down drastically, and this allows you really to run that. But as I said, for us it was technologically completely new. Meanwhile, we learned it. And so this is also progressing very well. A lot of the components which go into all these buildings have already been built. We have a large storage area where all the stuff is being stored, and constantly we get new things in. What is also interesting to mention is the computing. We have a high power computing system, the Green IT Cube. It's called Green because it's very energy efficient. This is again this factor of electricity. It's very compact. It has a 3D construction, which was optimized for shortest signal lines. This is good for computing, but also good for reducing the power consumption. After all, we have something like 300,000 CPUs in this cube here. This building is 10 by 10 by 10 meters. So a rather compact one for 300,000 CPUs and 100,000 terabyte of data storage, and you can digest 1 terabyte of data per second. So now the physics you can do with FAIR. We divide it into 4 parts. One is NUSTAR, which stands for Nuclear Structure, Astrophysics and Reactions. and we would like to understand stars and nuclei. And this is about 900 scientists. Unfortunately enough, also a lot of scientists here from this institution. Then we have CBM, which stands for compressed baryonic matter inside neutron stars. So this is around 500 people. PANDA, anti-proton annihilation in Darmstadt, so research with antimatter, again around 500. And then a compendium of a lot of other things, which is coming together in APA. So this is atomic physics, plasma physics and applications, medical science, all this. Their motto is from atoms via planets to cancer therapy, and this comprises something like 720 people. So you see, this is a fairly broad distribution of activities, and I will concentrate today on my favorite, which is NUSTAR. And to give you a feeling of in which direction we are heading, what we want to do is, after all, we think that with such a facility, you can study cosmic matter in the laboratory. So, and to give you an idea of that, you may all remember this event where for the first time gravitational waves were detected in 2017, which was coming from the merging or the collision of two neutron stars. So this was such a strong impact that one could measure the gravitational waves, and at the same time we were able to really see where this event happened, because one could also see the X-rays and the gamma rays emitted in that point. So this is an artistic view of this, how it could have looked like. The interesting thing for us is there was some prediction of JSI theoreticians how the light curve, which is then the intensity of the X-rays and gamma rays over time, would evolve. And this is what they have predicted. This is this blue line here. And what was actually measured then after this merger was the red dots. So you see it's fairly well. And what is behind this blue curve is a theory how the heavy elements were built in the universe. So far, we do not know how actually everything which is, let's say, above mass 100 or so was produced. There are theories for that, but there was not a possibility to really understand. And what we now think is, first of all, we believe now that we found the sources which are these kind of strange interactions of merging neutron stars, which produce a lot of heavy stuff, as lead, uranium, gold, whatever. This is produced in such events. But what if we want to understand this in detail, we need to know the nuclear structure of the isotopes which are produced in such an event. This is what we can study on a very small scale, but nevertheless in a sufficient scale that we can extrapolate from our laboratory to this gigantic astrophysical processes. This is what we do, what we want to do in NUSTAR. So, and to bring it more down to earth, so this means studying exotic R process nuclei. So this is rapid neutron capture, which goes in this direction. Also one adds neutrons to a nucleus, and then it gets more neutron rich. And this process depends then on the nuclear structure of all these isotopes. And this is what we want to study with our system. But that's not the only thing what we want to study. Finally, with such a nice facility, you can do a lot. And so this is our basic questions we would like to answer with FAIR. What are the limits for the existence of nuclei? Which means where are the proton and neutron trip lines? And where does the nuclear charge end on the top end? What is the heaviest element we can produce? So how does the nuclear force depend on varying proton to neutron ratios? What is the isospin dependence of the spin-orbit force? How does shell structure change far away from stability? We know that the normal shell model somehow collapses if we go far away from the stable nuclei, and we would like to understand why and how to explain collective phenomena from individual motions. There is lots of new ideas, lots of new shapes, what we expect, pyramidal shapes, hollow nuclei. All this could be, if it exists at all, as theoreticians are good in inventing new fancy structures, but we have to prove now in the lab that they really exist. And this, if one would have a chance, then certainly only one facility like that. Then we ask ourselves, how are complex nuclei built from their basic constituents? So what is the effective nucleon-nucleon interaction, and how does QCD constrain its parameters? And this leads also to the other pillars, to CBM in particular. They understand, but they investigate also QCD, and maybe there is some overlap here. And finally, now coming back to what I started with, which are the nuclei relevant for astrophysical processes and what are their properties? So what is the origin of the heavy elements? This is our main story and our main task. So now you may answer, but you may question, so how can one get answers? So after all, if you want to get answers, then you have to study the properties and the behavior of exotic nuclei. That means not only the ground state, but also the ground state masses, binding energies, spins, parities, whatsoever. But you also need to understand excited states. So the energy, spins, moments, and transition probabilities from excited nuclear states. You have to understand the decay of exotic nuclei. So the lifetimes, the energies, the decay modes, all this needs to be understood. And also the reaction. So how do nuclei react with each other? What is the kinetics? What is the energy needed? What are the constituents of these reactions? And one has to investigate this systematically with many isotopes for stability. So in particular, nuclear structure physics is always, not always, but sometimes criticized to be something like stamp collecting. But this is not the case, because if you do not really get a fairly good overview of all the nuclei, you will never understand the behavior of the nuclear forces, and therefore it is possible. So this is the kind of work we have to investigate and to do to really get the answers. And this is how we see how we get the answers. So as you can imagine, this is not a single experiment. It's also a lot of complementary experiments. And therefore, in NUSTAR, from the very beginning, we thought we should cover each and every aspect of nuclear physics, whether it's decay spectroscopy, which is in a project called DSPEC, whether it's electron nucleon scattering in ELISE, which comes in a later stage because it's more complicated. We would like to investigate light ion scattering reactions in inverse kinematics in EXL, which is also somewhat later, not in the first years of FAIR. Then high spec in-beam spectroscopy, then ILIMA to measure masses and lifetimes of nuclei in ground and isomeric states. We want to do laser spectroscopy in NASTIC. We want to make precise mass measurements with traps and MUDs. We would like to make kinematically complete reactions and understand them at rather high energies. So this is R3B. We have to produce our radioactive beams. We need to identify and to do spectroscopy. This is done in the super FRS. And finally, we also included the super heavy element program of JSI, also where we will not take advantage of the new FAIR facility, but at least in the beginning, we will stay at the UNILAC, so it's the existing facility of JSI. But nevertheless, as I said, we also would like to understand what is the far end, so to say, what is the heaviest elements one can produce. And physics-wise, of course, this is strongly interlinked. And therefore, one also has to include this. So, and as I said, what we aim for is complementary measurements with all this suite of different setups to get to consistent answers. Now, Obviously, this cannot be done by a small group, so you really need this huge collaboration, and that's what it is. It's the largest nuclear physics collaboration in the world. Currently, 184 institutions are involved from many, many countries. And our approach is kind of evolutionary. We want to advance instrumentation by continuous development and gaining experience by physics exploration. So we will not stop now with a certain suite of detectors and setups we have, but we are on the way. Every 5 years, 10 years, there will be a new generation of experiments just to really go deeper and deeper to what is technologically wise possible. This is all what we want to do. And so currently we have more than 50 major instrumentation sub-projects for the first stage, which is this modularized start version of FAIR, which should be ready then in, let's say, 3 to 5 years or so. And we have several thousand major components. So this gives you a feeling of how big the whole thing is. This is our playground. We have the super fragment separator, which is the working horse, so to say. With that, we produce all kinds of exotic nuclei. Then we have 2 experimental caves, the low energy cave, which is shown here in green, which houses nuts and glass spec and high spec and E spec. Then we have the high energy cave, where we go for really highest energies for R3B. And then we have the CR, the storage room for ILIMA. So this is where we want to work with. Now you may ask, well, why do you think that with your fragment separator you are somehow unique? There are competitors in the world. So you know that our IBF at RIKEN is available since several years, and just now EFRIT at MSU in the United States comes online. But the difference between these 2 facilities and the FAIR facility, as the Super FIS, is very limited in energy. So we can come up to, let's say, 300, 400 MeV per nucleon maximum. And if you want to produce fully stripped ions, that means bare ions without any electrons left in the as an atom, then you have to have rather high energies. And so with 400 MeV, you come roughly to something like Z equal 50. But if you want to go for the really high sets, as heavy elements, you have to go to higher energies. And this is shown by this curve here. So if you want to have uranium naked, then you need optimally 1.4 GeV per nucleon. And this is not available at those facilities. And this is where we are unique. That means, in the end, what we are aiming for is all this area here, where we would like to concentrate our studies. Also, there is a lot of things which should be done also in the domain of lower energies, lower masses. At least, let's say, we have competitive intensities to throughout the periodic table to also contribute in this area. And 2 facilities, those 2 in the world, is anyhow not sufficient for all the experiments we are aiming for. So, and the other point is this increase in intensity. Currently at JSI for our experiments, we have a uranium beam with 1 to 2 times 10 to the 9 ions per spill. And the spill is typically, let's say, 2 seconds long, or can also be shorter. And here you see the upgrade measures we are going to perform now. And finally, with this 100, we will come to 3 times 10 to the 11, or meanwhile, we even believe that we can reach the 5 times 10 to the 11. So that's also a major upgrade in intensity, which helps a lot together with the larger apertures of the superfragment separator to really get a higher throughput. And this makes then finally the 10 to the 4 intensity increase of some of the most interesting isotopes we would like to study. And in addition, one should also mention this figure here, because of the 6 stages of the Super FIS, we can have very clean beams. So all the chunk one is producing in such fragmentation reactions leading to the isotopes, which is enormous here in Z over N. This is just an example here. This can be really nicely reduced by all these stages that in the end one really ends up with the beam of interest model. So what will be the highlights of the initial phase 1 program? So phase 1 means that we start experiments at the FAIR facility. So that we might cover the first 5 years or something like that. So first of all, we would like to understand the third R process peak by means of comprehensive measurements of masses, lifetimes, neutron branches, dipole strengths, etc. along the N126 isotopes. If I go back here, this is this thing here. So the rapid neutron capture process, this is what theory predicts where it should go along. This is more or less the process which produces these heavy elements somewhere up here. And particularly interesting is this waiting point area here. This is what we would aim first for. And this is one of our 3 core experiments we would like to do. Another one is the equation of state of asymmetric matter by measuring the dipole polarizability and neutron skin thicknesses of heavy ions and heavy elements. And finally, to study exotic hypernuclei. At these high energies, you can also go for hypernuclei, and particularly outside the stability region again. So this is doubly exotic hypernuclei, so to say. Now, what about this N126 physics? So if you look at the abundance distribution of elements, heavy elements in the universe, then you come up with this measured points here. And theory now tries to understand how this intensity distribution was produced by this R process. And you see here the old predictions from theory in black and some new predictions in blue. And instead of getting better, it's even getting worse. And it was, for some time, it was not clear why the theory could not predict at all this third R process peak. Meanwhile, we have several ideas. So it could, for instance, be due to the neutron branching, that we have some neutron decay instead of the normal beta decay, what you would expect in this area here. So what we would like to do is to measure the masses, beta lifetimes, these neutron branches and strength distributions, and also the particular level structure of isotopes in this area. And of course, in the first phase where we do not, this phase 1, where we do not have highest intensity yet, we cannot reach down to this really interesting area, but we have to make it step by step. But as I said, we anyhow have to study a lot of isotopes to get a full picture and a full understanding of the whole thing. Therefore, it doesn't matter that we cannot reach in one go now our dream nuclei, so to say, but we have to start fairly modest. This is what we are doing in phase 0. So phase 0, by the way, this is the experiments we are doing at JSI with new NUSTAR instrumentation, while then from 2025 on, we enter phase 1, and this because then we can use the super FPS as a production tool for our isotopes. This provides then access to this area here, and in later phases where we have then the CIS-100 available and later even CIS-300, then we can reach this area. So this is what we do here. Then, I mentioned the dipole strengths, also the equation of state, and there we want to advance the energies. So right now with the FRS and with the magnets used at, for R3B experiments, we cannot really go very high in energy. So we can study nuclear excitations up to 5, 6, 7 MeV. But we would like to go higher, and if we aim for 1 GeV per nucleon beams, then we can really reach this part here. And the same is with equation of state, where we can study the low-lying E1 strengths at much higher masses, very heavy ions. This is what we are aiming for in this field. And then finally, I mentioned the hypernuclei, and there we have also, this comes also in stages at JSI, and this is just an experiment which ended last week. We can produce now proton-rich hypernuclei, so covering this area here, but then as soon as phase 1, which is here called phase 2 of the hypernuclear project, if this comes available, then we can also go to the neutron-rich part here. And at a certain stage, if this is successful, we are dreaming of their own hypernuclear separator, and then they can really go very exotic. And this is their aim. Good. So now, with all these numbers to come back to where we are. Right now, we are running phase 0. And there I have to tell you a rather sad story. So we were doing experiments at JSI until 2014. And this was the time where FAIR was in a kind of crisis, because we were not able to build it according to our plans. So there were delays, there were cost increases, and so on. And therefore, BMBF, also our research ministry, they said at some time, now you stop doing physics, you all concentrate on building FAIR. And even if you're a nuclear physicist, you have to build FAIR now. And, this was a disaster in a way for us, because we are no engineers. Nevertheless, we were asked to contribute, and so we did. And we had to give up all nuclear physics for several years. And we told the ministry, oh, this is not good, because then we lose, within a couple of years, we lose all our expertise, because people will leave. Our young generation, which holds more or less their expertise and develops it further, will not even come. So there is a gap of 2 generations of PhD students. And this is not possible that we can resume then afterwards as if nothing has happened. And we have a nice facility, but we are no longer able to do physics with them. And after 4 years of begging and massaging our ministerial people, and with the help of our new managing directors, which you saw 2 weeks ago, we were able to convince the ministry that they understood that we have to continue. And in 2018, they allowed us to go back and do some physics, of course, on a reduced scale. So we are running the JSI facility for 3 months per year at the moment, but nevertheless, this is now guaranteed until FAIR is ready, which is supposed to be into the end of 2025. And this time is what we call the phase 0, and there we do both. So we do experiments with the already existing equipment of NUSTAR. It's getting better and better, this equipment, because we are getting more funding, we get new ideas. But we always can use these machines, the GSI, to do the commissioning, to do first physics. That's what we are doing right now. And at the same time, in parallel, we do the civil construction of the NUSTAR caves. We do the construction and installation of super FRAs. And we hope that we can start with commissioning in 24. And then the first part of it will be ready then in 25. This is what we call the early start, 25, 26-ish. Then commissioning is done, and then we can really enter phase 1 with what we then call the day 1. And then we run these experiments. And as I said, this will take another 3-4 years or so. Then we enter at around 2030, the second phase, then phase 2 of FAIR, but this is future music. So how do we see this startup? Here you have again the facility. So we would like to do early physics here in this place, which is just the main straight section of the super FRS. So it ends here and it goes into the high energy cave. So here there will be two experimental areas, two focal planes of the super FRS where one can do experiments, and this will serve the super FRS experiment collaboration, D-spec and R3B. And as I said, this should, what we are aiming for a start in the fourth quarter of 25. Then the next one is then in 26, 27 that we get the front part of the low energy cave ready, which means more magnets to be installed and commissioned. And this will then house Agatha, which is a germanium array, another multinational array in Europe, which comes then to JSI for several years. And then by 2027, the whole low energy cave with the bunch of spectrometer here, the additional magnets will become ready, and hopefully we will have also the additional funding for ELIMA, which is then which is the ring experiments also in 2027. And this initial thing here, we can even start with this 18 beam, so we can, there's a direct connection from this 18 to the super FRS. We do not rely at that point already on this 100 operation. That means in parallel to us taking the first beam, we will still work on completing and commissioning this 100, but we assume that sometimes in 26, this 100 operation with then much higher intensities is possible, but still we could run the first experiments in 26, 20, up to 27 with this 18 beams if needed. Only then in 27 it must be established, because those experiments here they really require highest intensity, and also the Akada program, which of course runs for longer than only 1 year. And so this will require then higher intensities. So I think we are on a quite good way. So here you see the construction site of our core, so to say. These are the NUSTAR buildings. This is one of these nice views where you can get all around an image. This to the left here, you see the high energy cave. This is inside. This holding structures are because there was this is freshly poured concrete ceiling of the cave. So this one is ready. Meanwhile, we are out, of course. Then here, this area, this is the low energy cave, and this part here, this now seen from the other side, this is our NUSTAR and Super FRS control building. Most of this stuff is really underground. You can figure it out here. This should be free, so we are below ground here. And only this building will look above ground, but all the rest is underground. This is for radiation safety, which is in Germany ridiculously strong, so we are not allowed to go above ground with our new experimental areas. Also, there is no big radiation coming out. So we measure the progress in the NUSTAR project by what is called an S-curve, which is how many milestones of the project have been achieved, and we have several hundred milestones. And meanwhile, this is what we have in green here. This is achieved, so roughly half of all the milestones. This is what we still need to achieve by the end of 26, 27. In red, you see this was our planning, or it is still our planning, and we follow the plans quite nicely. So what one has to say, there is only a minor impact from COVID-19 so far. We were expecting to have a stronger impact, but this seems not to affect us at all. However, there is now consequences of this Russian freeze. They are being investigated, so we have started a task force for that, which looks into the implications. Russia, as the biggest share or the second biggest shareholder, contributes, of course, in each corner of FAIR with something. And concerning NUSTAR, they contribute to the front part, also the first stage of the super FIS. They contribute considerably to the cryogenics, also cryogenic parts. I told you that we run everything superconducting, and there they are heavily involved. They are involved in some of the experimental components. But what we figured out in the last 2 weeks is technically it would be possible to start our early science still in time. So we can still follow these plans. There are companies ready to take over. It's only a matter of finances. And the last number what I got from yesterday is something like 15 million euro extra we would need, which is in the noise of the cost. So I told you we are close to 3 billion meanwhile, so 50 million more or less, yeah. But still we have to convince the other shareholders, and in particular our research ministry, to give us all this money. But if this comes within this year, then we can, despite the Russian freeze, we can continue as planned and do the first experiments in 2025. So now what are our ideas for this early science? Also these first, let's say, 12 months of operation at FAIR. So in DSPEC, we plan to move our already existing and well-established setup, which comprises AIDA, which is an active implanter, with Degas and Fatima, which are germanium detectors and fast scintillator detectors. We plan to move this setup in the first quarter of 25, and then we would be ready by summer 25 and can start the first experiments. Until then, we continue our phase 0 runs until 24. So this year, next year, and over next year, we have ideas how we want to continue, and we have also some confirmed commitment from BMBF to fund all this, so this should be possible. R3B needs for their clad magnet and for their complex instrumentation more time, so we will already start in the first quarter of 24 to move the clad magnet. And nevertheless, we can do other experiments not requiring this magnet in their current cave, which is the cave C at JSI. So we also want to continue until 24 doing experiments, and then we move over and make commissioning like type experiments in the new high energy branch. Super FIS experiment collaboration. We plan to get their gas cell. This is an implantation cell where you can really select the rarest isotopes, the rarest species one can produce with the super FIS. So, and the main aim is really to find, first of all, and identify the isotopes. So this will be done also in front of the high energy branch in these early days. In 25, this is the only part of, or the only instrument which does not yet exist. So it's in construction and should be ready in time. So all our sub-collaborations have basic setups ready for 25, beside this one. The only thing what is missing is certain infrastructure items which are not yet funded. But there we had, 2 or 3 weeks ago, we had a meeting with the funding agencies, and more or less we committed them that we would pay for this infrastructure items as well. So this was the last hurdle, so to say, which we had to take. This is now also done. So in that sense, from our point of view, there is nothing which stops us from really doing experiments in 25 as expected. So now, well, I have a little bit to hurry up, but nevertheless to get you some feeling of what kind of, or how these experiments look like, how complex they are. Let me just give you one example, which is our DSPEC experiment, which stands for decay spectroscopy. So how is this done? In general, so we have a heavy ion beam of an energy of about 1 GeV per nucleon, shoot it onto a production target and do all kinds of reactions there, and fragmentation in particular, but also fission reactions. And then we have a set of dipole magnets and some wedge-shaped degrader, which allows us to transport and select certain isotopes out of this manifold produced whatever distribution of isotopes. So usually one is interested only in a few of them, and they can be separated and transported with such a separator. One wants not only to select, but one also wants to identify what one has selected, and this one does with a suite of scintillation detectors, the time of flight, multi-wire detectors, or other type of position-sensitive detectors, a music, which is a delta E gas detector. This allows unique identification, ion by ion, of the secondary beam. And then we know what we have produced, and then we shoot these produced ions, which survive this transport from here to there, into an active implanter. That is this AIDA, what I mentioned, which is again position sensitive, and then we wait for the decay. And once we have a beta or alpha or isomer decay, then it's associated with the emission of gammas, and those gammas are detected then with gamma detectors, and this is how we do our spectroscopy. So in principle, this is how all these experiments work. And of course, when we started again in 2018, 2019, we had to learn how to make this, how to operate such a system. So this you see in these figures. Unfortunately enough, we have really a lot of bright students and postdocs and nice people, like I think this is Jelena here, who helped us. And in a common effort, we really were able within 1 year to get it going again. And here you see how much hard work it is to shift the whole thing and to get it running. And in 21, then we were really ready for the first experiments, which we do right now in this phase 0 program. So we are quite happy with that, and we continue now also this year. So from this campaign in 21, this was essentially 3 experiments. One dealt with cooperating in neutron deficient tin isotopes. The other one was to investigate this area here, so southeast frontier of the A225 island of octopole deformation in these heavy systems here. And then it was also shape evolution below N126 in the Mars 190 region. So this was our first prize, and yeah, we were quite fast and efficient. So meanwhile, the first publications were even accepted. As one could imagine, first of all, one does some new papers for the technical stuff. This here is an important one, which was just accepted last week. So that's a DSPEC setup. So it describes the whole setup we are going to use right now and later on at FAIR. But there's also already the first physics paper coming out from this experiment. And we have now several in reviewing. So it will continue like that. And yeah, the predecessor project of DSPEC was called Rising at JSI. This was running for 5, 6, 7 years. And there we got something like 200 publications out. And you can imagine for this one, which is more complex, more powerful, we expect even more in the long run. But it's just starting. And there is, of course, Slovenian contributions to that. There is a beam quality monitor for the accelerator control made by Gregor. He is sitting here, and he is also involved in the BGO backcatchers for the Degas detector. This is a Slovenian contribution, but there is more to come. So we are also involved in you are also involved in R3D. This shows now how complicated R3D is. Essentially, you have a target which is this part here surrounded by a calorimeter, which is called Khalifa. And then whatever you produce, you deflect with this clad magnet, which is a superconducting dipole magnet. And the heavy fragments are deflected under some angle and can be measured then with some particle detectors. The lighter ones will be also detected under some larger angle. And the neutral particles, or the neutrons in particular, can be detected by a very large neutron detector. This is their basic setups. And their initial experiments was a proof of concept for P2P fission reactions, where they used Khalifa to measure the two protons in this reaction. Here you see the opening angle, so it's rather close, but nevertheless one was able to identify the protons individually, and then the fission products were identified here. And I think we used also Neuland, also this neutron detector, to get the associated neutrons. So that was this one. And another experiment was to identify the fission yields of neutron deficient actinides, and here you see the nice resolution for all these fissioning channels, what we produced there. So this was also a proof of principle for the clad magnet, and we are as us, so we are also very happy with all the progress we made, and so we are now ready for great physics. And here the Slovenian contribution was the construction of the 60 intrinsic phosphate IFOS detectors for this calorimeter Khalifa here. So this is a large contribution, also financially wise. And then finally, the SuperFS experiment collaboration, we have a broad science program, and you see it also on the many experiments we did. This is simpler experiments in a way, but nevertheless also important like ours. And they were now the first this year to start. So in their setup, this is the Vasa magnet, which we got from Jülich. With that, we did these experiments, which I mentioned before, and of course there are no results. We stopped last week, and now we dismantled the setup, but it was quite successful. And the next people to run is now R3B, and high-spec or D-spec will run in about 4 to 5 weeks or so. So that's the plans for this year. This I should not skip. Yeah, it's a Slovenian contribution also here. It's a stabilization monitor for electrostatic lenses for the SuperFS experiment. So that's more for the future, but it has also been tested meanwhile. As you see, Slovenia is engaged in NUSTAR in all aspects. So finally, and here I really don't have the time, unfortunately, for that. It's from these NUSTAR projects, we get also a lot of applications. Within the projects, we develop detectors, we develop a new methodology and new analysis techniques, but all these ingredients, they can also be used to invent smart devices. In particular, and this is new now, and this is where we put a lot of emphasis, is artificial intelligence and machine learning. And this will then lead to applications. So in the past, we invented a very sensitive medical gamma probe for cancer investigations. We invented a landmine imaging detector. We invented a dirty bomb finder. So this is all part of our activities. Unfortunately, as I said, I don't have the time now to go into that, but I can tell you there is many more ideas, and it's of course also welcome to come up with new suggestions what one can do with all this. And this brings me now to the conclusion. So I hope I have convinced you that NUSTAR at JSI and FAIR enables unique and important contributions to our understanding of the atomic nucleus. The planned and available instrumentation is indeed state of the art. and will continue to be state of the art because of this evolutionary process I explained to you. Execution of NUSTAR phase 0 experiments at JSI has started recently and is not, some slightly hindered, but not really stopped by Corona. A strong experiment program with more and more of these novel detectors is planned for the coming years, and we will start, if everything goes well, at FAIR in phase 1 in 25. Slovenia is an important collaborator to NUSTAR, but further enhanced collaboration is of course highly welcome. And there are various fields of engagement. It's of course physics, both in experiment and theory. Our theory leg is somehow lagging, but also in instrumentation development, in infrastructure, in particular also in applications. And with that, I would like to end and thank you for your attention. Yes.
So Jürgen, thanks a lot for very nice and informative talks. I would first like to invite audiences.
Jürgen, for this very nice presentation. Just one comment. You showed the elemental abundances to illustrate the third art process. These were not abundances in the universe, but solar system abundances. The abundances in the universe would be quite difficult to define because they are changing all the time.
Yeah. Okay. Yeah.
Thank you. Further questions?
Thank you for a very interesting presentation of past and future. I have a question. Somewhere in the beginning, you showed a power law behavior of the luminance in measurement, which you said was understood by theory. The power law was called minus 4/3. What could you tell us, or maybe you can start with, could you tell us what are the processes involved? I mean, the idea I understand is to learn from accelerator experiments about exactly such processes. So my question is, what are those processes?
Also the reason why it went like that is you have to imagine that in this environment where one produces these exotic things, it's rather hot, and therefore you would not produce by just adding a neutron, you would not produce a new isotope and then it sits in its ground state, but it's in excited states, and so you have to understand all this dynamics which is behind that. If you have then a system where you are not in an equilibrium, but which is in an excited state. And in this instance, you have already the next neutron approaching. So you add another one, heat it up even more. All these, this is what it goes into this process, what I understood from the theoreticians. But in detail, I can't tell you how they do it and why they come to this this power law at all.
Okay, now, the power law is common in nature, so usually
this is what one would expect somewhere.
Right, so I was just wondering if there's a well-defined process for that. A very different question, if I may. What do you anticipate the annual budget, the running budget, to be in, let's say, year 27 or 28 when it starts running?
Yeah, also we just recently made a survey. We made it already in 2012, I think, or 14, but we reconfigured it, reinvented it now, and we come up to something like 200 million per year. This is the budget for such a big facility.
Okay, so that's how many hatches or how many teams is that? Approximately, well,
people-wise, so it's not so many more. So we expect to get an increase. We are right now in the science division. We are around 160, 200 people, and we would expect to get another 60, 80, something like that. What is more is the accelerator part. They are also around 200 and they want to double. But their funding agencies said already, you're crazy, you should go down, and maybe we come up with 300 to 350. One way out would be that we hire people from outside, particularly for maintenance, and so that this goes to companies, because they are afraid that we have finally 2,000 people on ground, and this way they don't want to finance.
Thank you. Any other questions from the audience, or should we proceed? Okay.
I was happy to see that you have ELISI on your list of experiments, and I was wondering when this is foreseen and what kind of electron accelerator ELISI will be. Thank you.
Elise, sorry. What kind of electron accelerator? Wow, it's a linear accelerator which runs in parallel with stored ion beam. In the details I would need to look up. But when, this is a good question, because this is also only financial question. Technically, we would be able to do it. And in our planning, it's in phase 3, so it should come second part of the next decade. So 35 to 40 it will come. So you are still young enough, you can take part in these experiments. But this is also an existing collaboration, and also we cannot do a lot of physics at the moment. We are quite riveted, so we are open also for new collaboration.
So we have also some raised hands on Zoom, so we can proceed then with the questions from Zoom.
I guess it's me who has the raised hand. Okay, if you go to your slide 26, your S curve, I wonder, because, I mean, COVID has plagued the collaborations quite heavily, and you seem to be almost untouched by that. Is the reason that you do most of the things in the lab itself and you don't rely so much on contributions from the outside labs, and that there are not so many interdependencies?
No, also we have a lot of outside activities, but what we learned is to really work remotely. Also, we love to collaborate and to work together. In this crazy times, it was of course not possible, but to our surprise, it was not only that people at JSI continue to work, working at home, working in the lab under harsh conditions, but nevertheless, and this was obviously also the case in many of the other institutions. So there was not really a shutdown. And what one should say also, we are at the moment, we are mainly driven by finances. So if we get new money in, then we can buy new stuff and then we can produce things. Unfortunately, this is much slower than what we were hoping for. And maybe this is also the reason. This curve is not very ambitious. So in principle, we could, if we would get more money, we could be even much faster. But this is dictated by the funding processes in the various countries, because we do not have a lot of basic funding from FAIR. So FAIR gives us 78 million euro for all the four research pillars. So we have, I don't know, 22, 26 million or something like that from FAIR. But our equipment costs around 100 million. So all the rest comes from institutional funding from all these 39 countries. And whenever an institute gets some funds, then they can contribute to something. This is how we unfortunately have to open.
Yeah, but that's quite normal in collaborations like that. I mean, I would even say that the level you get from FAIR is quite fair. Let's put it that way. So, because, but I'm still very surprised. I mean, also the fact that you fit so well on your predictions and so on. I mean, is there some rebaselining?
Yeah, of course. This one also should say, also if you compare it to the one which we made before 2015, then this looks completely different. In 2015, we were assuming that we would run in 2020 already. And but what I can say is we made a new version in 2016, and this is fairly unchanged. Also some details, some kinks in this curve has changed, but the overall structure is still the same. Also this is, I also have to admit, I was surprised that we are doing so well, but yeah, that's a fact. Due to all the distribution of our collaborators all over the world, this seems also to help.
Okay, thanks.
Any more questions from Zoom or from the audience? Any raised hands? No, so I will have then the last question. So can you tell us a bit, you mentioned CIS 300. So can you tell us a bit, of course, everybody will wait for the fair day one results, but when is foreseen to have CIS 300? So in what is like the time scale?
This is also in the 30s at some point. Here you see it. Also CIS 100 stands here alone, but in fact it's a double ring. So the tunnel is made such that one can occupy another ring, which is a stretcher ring. And this would increase for us, for NUSTAR, the beam intensity by a factor of 4. For CBN, since they rely on highest energy, they are not interested in this high intensity, but they would like to get then the beam energy increased to 35 GeV per nucleon with this 300. But at the moment, with all these cost increases, this is really in the stars. Officially, according to our planning, it should be around 35 or so, 2025. But if this ever happens, we don't know. And by the way, meanwhile, CIS 300 became a CIS 400 because the experts, the accelerator experts, found new ways how to increase the rigidity and how to occupy this in the space here. So it would be even higher energy if it comes.
Well, so thanks a lot. So thanks again, Jürgen, for this very, very nice and informative talk. And for the rest of the audience, we will have these seminars once per month or bi-monthly with the distinguished lecturers from all the 4 FAIR pillars. So thanks so very much for your attention.